Welcome back. So this is lecture 38 in this course, and we will continue with Hamiltonian Monte Carlo sampling. So we will take an example and see how HMC sampling works, and then we will also take a look at that how to implement, or let's say how to use BRMS library, right, for estimating posterior distributions, or basically for parameter estimation using HMC sampler, using HMC algorithm, because this PRMS library uses HMC sampler in background. Okay. So the algorithm it implements for computing the posterior is the HMC algorithm. Okay. But first we will continue with the example that you were taking in the last lecture. Okay. So in the last lecture we had a HMC sampler. So basically first we analytically derived the gradient for mu and sigma. So basically we analytically derived what would be differentiation of potential energy function with respect to mu and sigma. And what was potential energy? It was negative log of likelihood and prior. Right? So that we have written here, and this potential energy function actually gives you so this function gives you potential energy of current state of the chain. So basically it is calculating negative log of likelihood and prior. So I can also write it here, negative log of likelihood into prior. So this is what this function is giving you, right? This gradient is actually gradient function. It gives you rate of change in momentum with respect to time. Okay, and what we are differentiating here is actually kinetic energy. So it's basically differentiation of kinetic energy with respect to position. Okay, so let me write x, position. So that's what we are doing here. All right, so once you get this gradient function and potential energy function, now you can go ahead and implement your sampler. So let's say this was our data from a normal distribution, and this is our model. So our likelihood assumption is this, that each data point comes from a normal distribution, and then we have two parameters, mu and sigma. Prior on mu is normal ms, prior on sigma is normal ab, and the priors are listed here. Okay, so this is just, we are setting up the model here and the data. Now we define this HMC function, and last time I think, if I remember correctly, we tried to run this, right, but this was not working properly and it is giving us NAs. So there was some problem that we need to fix. The problem is, so actually we are getting a lot of NAs after some point. So we could initialize the chain, so that is not a problem. So we could initialize the chain. We could also generate a new proposal, and that we also accepted, right? After that, nothing is happening, right? So after chain initialization, so the step that we have missed here, the one that is causing the problem, is this, that we haven't defined a loop for evolving this Markov chain. So that you're updating I, the current state of the chain, every time, so that in next step the I gets updated and you start sampling again, right? So you're not doing any further sampling anymore. Okay, you're not doing any sampling at all. So after initialization, right? So you need some loop here. Okay, so you need to iterate through these steps again and again. So you have followed these steps of current proposal, then basically current state to new proposal, and acceptance or reject, but you haven't iterated through all these three steps, right? So for that you can define a while loop, right? So while I is less than, let's say, number of samples, right? So this will work. While I is less than number of samples. So all these things should be inside this loop. Now this is good. Now I think this should work. So let me now draw samples using HMC. So see, it took some time. So that means it did some sampling. Let us draw the histogram. Yes, so it did some sampling. So see, this is the posterior distribution it has estimated for parameter mu. Let us see posterior distribution for sigma. This is posterior distribution for sigma. Okay. I think initially the sampler started from somewhere and then it is taking some time to reach the high posterior density region. So maybe we can have a burn in here. So we can throw out first few thousand samples and just rely on remaining samples to estimate our posterior. So let's say throw out first 2000. Okay, so I will consider sample number 2001 to 5000 as my actual samples, right? Yes, this is better. So basically you need burn in because that can happen sometimes in certain algorithms or in certain cases. You start from a very wild place and then it takes some time to reach the posterior density region. So the convergence might take some time. So that's why we call this period burn in period or warm up period, right? So chains are warming up. Okay. So once they are warmed up, they have reached their place, then you can basically consider sampling. Then you can consider them as valid samples from the posterior. So it is working fine after 2000. I think it will also work fine after 1000. Yes. After 1000 there is some problem. I think there are still few samples which are in that range. So this is what you can do. But of course, things can get better if you just change the step size and number of leapfrog steps, right? So those parameters still need to be adjusted, okay, even for HMC. So all that's a really good algorithm, but those still needs to be updated. But the reason why we say that this algorithm is better than MCMC is this, that this algorithm would always have a considerably low rejection rate, right? So let's say I'm running it for 5000 iterations. Yeah. Let us see what is the rejection rate. Oh, why it is 0? See, the rejection rate is too low. It is 0. It's surprising. You're not rejecting any sample at all. What happens if I increase the step size? It's still 0. Start with reject 0, then inside while loop reject equals to reject plus 1. Okay, now you get some rejection rate. Okay, and this is 0.00, so basically 0.05. So that is the rejection rate, that much percent, 0.05%. That's too low. Now so sampler is also better actually. I think we would want to visualize the sampler. So I should use zzplot chain 1 samples aesthetic sample ID 1, 2 and iter. Can also store step size. So let us plot this. Post samples x equals to sample ID. On x-axis we want sample ID. On y-axis we want mu and sigma. So let us just observe mu first. Then you can group by step size. You can, by the way, run multiple chains as well. Geom line. Okay. So let us see how the sampler evolves. What happened to ggplot2? Okay, see. So this plot shows the sampling, right? So I plotted this point plot, so it might look slightly weird. But what happened here is that the sampling started somewhere here at this point, and it quickly converged to the actual posterior. So I think it just took 100 or 200 samples to reach here. Okay, so it very quickly converged. So I think that this is a good step size parameter. Compared to this, let's say if you take 0.01, I think that was creating some problem. Okay, so rejection rate was 0 for this case, and let us see how the plot looks like. So this is how the plot looks like, right? So basically this chain was not converging at all, right? So it took 4,000 samples to reach here, right? So this was really bad. So it was too low step size. So step size parameter can still cause problem in HMC as well. What happens with 0.5? It gets slightly better. I think it's quite better with 0.5, but it's still the chain looks slightly weird. So sometimes it goes up and takes some time to come backwards, right? So it could be definitely better with 0.1 or so, right? If you do 0.5, I think that is much better than any of the others, right? So now it looks really good. Okay, and what is the rejection rate when you have a step size of 0.5? Now the rejection rate is 0.45%. So this is good. So the point is that the you used to get this good sampling, basically such good mixing and basically such good convergence with a rejection rate of around 25% or 20% in MCMC. Now you are getting that really good sampling, basically really good convergence, even with a rejection rate of 0.5%, right? So basically this sampler has this property that it would always have low rejection rate. So it's a much efficient sampler compared to a simple random walk algorithm. So let's see what happens if I take a step size of 1. Okay, now it takes time because I think now the rejection rate is quite high with the step size 1. It is taking a lot of time. So I think it could be now 45% or something, don't know. By the way, in this case, you have two parameters, right? So for two parameters, it should be anyway, the rejection rate is anyway would be large in MCMC sampling. You can also, by the way, decrease number of leapfrog steps. I think 12 is reasonably fine. Having less than 12 is not a very good idea. Basically, then the discretization is not good enough, or basically you can say that amount of time you are giving to observe the particle becomes too small. So I think 12, 15, 20, that's usually I use. But once you start using BRMS package, then you don't need to worry about this. So the default parameter setting in BRMS is quite good. Okay, that's not working. So let's see what it is right now. So it's a previous one. So sampling was not complete. So maybe 0.7 or something. It is now taking quite long. So chains are perhaps too many samples are getting rejected. And this can happen sometimes. So maybe I will stick with something like 0.25. Okay, so now see the rejection rate is around 0.1%. And I think samples will look fine. Samples look good. No problem here. I think even at 0.5, they might look good. It looks fine at 0.5. You can increase the number of leapfrog steps, so that can also adjust. It's really good at 0.5, step size of 0.5, and number of leapfrog steps 20. The rejection rate here is 0.57 or something. Okay. Now you do not need to burn in too many samples. Even if you, let's say, start at 101, you will get really good posterior recovery. See, no problem. Let us see the effect of step size parameter in the same way as we did for MCMC sampling. So we can generate multiple chains, single chain, but multiple chains. So let's say this was chain 1. Let me generate chain 2. Then chain 3. Chain 4. It is sometimes getting stuck. One possible reason why it might be getting stuck is this, that because the parameters that we have, so one parameter is mu, another parameter is sigma. Sigma is the standard deviation parameter. It has a constraint that it cannot be less than 0. So if it happens that during proposal generation, if the proposed position of sigma turns out to be less than 0, then basically your sampler will break, right? So one thing you can do is to ensure that sigma never goes beyond 0, and that's very important, otherwise the sampler breaks, right? So you will see later on in BRMS as well, it becomes very important to specify constraints on your parameter space, right? So what can we do here to ensure that this does not happen. Q. So what we can do is this. If, let's say, this thing, if Q plus step P is greater than 0, only then you do this update. So there could be a better way, but this is just a patchwork for now. Else keep Q as Q as Q. So if, so basically this is about Q2, right? So Q2 P2. If Q2 step into P2 is greater than 0, only then you'd make this update. Now it should work. Okay. And rejection rate in the last one is 0.25%. Posterior samples. Okay. So now you have, now you can do R bind. Okay, so one thing else you can do, post samples. Chain ID, chain was 1. Okay, or you can visualize each chain separately. So this is the first chain. This is the first chain of mu. Let us see the second chain. So the first chain is started somewhere below here and then went up, and then it converges really fast. Second chain also converges really fast. So this you should expect for each chain, and they should mix well as well. This is third chain. This is fourth chain. I'm sorry, so momentarily the ggplot function is not working on the system, but you can take a look at yourself. You can use the same ggplot functions that we used in the MCMC sampling lecture, and then draw all these 4 chains on top of each other. So you can, so this is a homework for you. So draw the trace plots. Those are called trace plots. So you can draw the plots of each Markov chain from this HMC sampler, right, on top of each other. So sampling is working fine when a step size 0.5, but when it is 0.05, then things will change. So let's say this is chain 4. Chain 4 looks like, so sampling is happening. So this is how chain 4 looks like. So it took almost 300, 400 samples to reach into that high posterior density region. And sometimes it can take even more. This is what happened with chain 1. Let us see what happens with chain 2. Chain 2 looks like this. Okay? Chain 3 looks like this, and this will look even bad if we take 0.01. So step size that we have changed now, it's 0.01. This is how it looks like now. So this is chain 3. This is chain 1. This is chain 2. So basically chains are getting stuck, and samples are correlated. So basically chains are not mixing well, so the model is failing to converge, right? So one thing that you can test for yourself is this, that regardless of how large you make this step size, rejection rate is still remains quite low. Okay, so you will, as you are increasing step size in this particular case, you are the convergence is increasing, right? You are getting really good well converged model, well mixing chains, right? So that is happening at a step size of 0.1 or 0.5 or so on, right? So between 0.1 and 1, so you are getting really good convergence, but still the rejection rate is quite low. So that is unlike MCMC. So in MCMC you will get a rejection rate between 20 and 50%, especially for two parameters you might get a rejection rate of 60%, but that is not the case here. See, so let's say I take a step size of 0.5. What is my rejection rate? 0.5%. That's too low. If I take a step size of 1, basically it is supposed to reject now a lot of samples because the step size is too large, but still rejection rate is just 3%, right? What if it is 2? Now rejection rate is slightly higher. It is taking time. See, sampler is taking time. Let us see how much. Okay, perhaps it is again getting stuck somewhere. Let me go with 1.5 first. So anyway, you can run it for yourself and you can check with different step sizes. You will observe that rejection rate will remain really low. I mean below 5% or 10%, right? And that's a very interesting and very useful feature of HMC. So the idea is this, that proposal generation is so good that you do not reject too many samples, right? Okay. Now, one thing I wanted to show you quickly in this lecture was this, that you can do all this, you can implement an HMC sampler without this all complicated code using a ready-made package called BRMS, which is available in R, right? So how to use this package? So it has a certain syntax which is suited for linear modeling. So you might not find syntax very intuitive, but let me show you that you can do the same thing using this. So let's say this is your data. So I'm storing the data in this data frame. So y is, let's say, some data from a normal distribution. So same data that we used for HMC sampling. Okay, so same data. So I'm storing the data here, and then I use this function BRM, right? And in this function I write it like this: y is predicted by some distribution, and the distribution is given here, Gaussian distribution. So that's my likelihood assumption. Okay, and then I set up prior assumptions. So on intercept parameter I'm assuming this prior, normal 1000, 100. On sigma parameter I'm assuming this prior, normal 10, 2, right? Then you can define other things here. So number of Markov chains you want, number of iterations in each chain, how many samples you want to throw up as warm up, right? So 1000, number of processing cores from your computer that you want to use. If you use all 4 cores, basically all these 4 chains will sample in parallel. Okay, so it will show these messages that compiling stan program, which is a probabilistic programming interface in the background, and then it says it started sampling, and then finally when it is done you can plot this model fit object, and this will show you posterior distribution of all the parameters that you have. So this was the posterior distribution for parameter mu, this is posterior distribution for parameter sigma. Okay, these plots are the trace plots, they show whether chains are mixing well or not. Okay, so these are trace plot for the chains for chain 1 to 4. Okay, and this is really good because chains are mixing well. And you can also see the summary estimates here. This is not very useful, but this is what gives you 95% credible interval for mu, this is 95 credible interval for sigma, right? These are not important for now. Basically, this is giving you log of prior densities. Okay, so basically you can, so I have done the same thing. I have calculated the posterior distribution of mu and sigma for exactly same example using this function. So this would be much more faster as well as it would be easy to define, right? So for further on, for linear regression and for hierarchical modeling and other things like, so in the next part of this course, I'm going to use this BRMS package a lot for modeling, right? So I recommend that you install this package, BRMS package, right? So it is shown here. You install this package locally in your system and then start practicing with it. Okay, you can take a look at tutorials which are available online. So we will be using this package for further parameter estimation. All right, so thank you very much. I will stop here. In the next lecture, we will take a couple of examples using BRMS, and then we will start linear regression modeling. All right, thank you.